I am presenting this paper on fluid dynamics of trees in the hope that younger professional plant scientists will move these theories forward. My name is Charles Redmond. I am 93 years old. I retired from the Navy in 1945. My last year was in the liberation of the Philippines. I am also retired from White Sands Missile Range, where I accumulated 26 patents in various fields, such as instrumentation, electro-optics, radar arrays, receiving and transmitting radar transmissions for use in indoor testing of radars, long-wave imaging, optically generated rotation transducers, and more. I am also retired from New Mexico State University, where one of my many interesting projects was construction and test of solar-powered heat pumping, or heating and cooling. My subject this morning is fluid dynamics of trees. Trees are fascinating. Water in the pictured weeping willow flows up, sideways, down, transpires from the leaves, and sometimes flows into the ground, breaking the soil into its elements and carrying the elements into the tree, where some are used by the tree, some are discarded from the leaves. There is no hump over the root system. Therefore, roots are extracting all the soil they needed and the trace soil. I am contesting the teachings that water in plants is only liquid. Colleges of agriculture worldwide have been teaching cohesion tension and other techniques as means of moving liquid water up trees and other plants. These theories all assume that water is liquid. I am proposing there is an adsorbed layer of water attached to the capillaries by means of hydrogen atoms and converts that layer of water to operate like an ionized gas, which drags additional layers of water that are liquid by means of the second hydrogen and against gravity. This adsorbed layer of gas-like water is key to everything water does in plants. Liquid water by itself cannot perform any of the functions of water in a plant. Gas-like water always flows to points of lesser density. Therefore, when chemical conversions or cell constructions occur, the gas-like water changes form, lowering the pressure of the gas-like water, and more flows in. The roots are sources, and conversions are like sumps. This system is so simple it performs all the functions of fluids. From a slight tremor in the Mesilla Valley to the magnitude 9 earthquake in Japan, from a slight breeze to a mighty hurricane, from the cycling of subatomic masses and energy in an atom to the movement of massive objects in space, all nature follows laws of physics. Plants are no different. They also follow laws of physics. The law of physics states for every action there is an opposite and equal reaction. Transpiration pushes, not pulls liquid up, as taught in plant physiology. The vapor tables show that as pressure is lowered but is always positive, evaporation occurs at lower temperatures. There can be no high negative pressure to pull liquid water up trees as taught in plant physiology. The reaction between liquid water and carbon dioxide requires high temperatures and pressure. Reaction between ionized gas like water and carbon dioxide is by catalysis at low temperatures and pressures. During the early 1980s, we had a project to demonstrate a system for storing energy for the Pacific Northwest Laboratory, operated for the U.S. Department of Energy by Battelle Memorial Institute. This project was under the New Mexico Solar Energy Institute. The basic idea came from Bob Sabin of the Physical Science Lab, and Bob was the prime leader of the project. The work was done by New Mexico State University students. Two key students, Jerry Tyree and John Bauer. I was very fortunate to have them on my team. The concept was quite simple. A system was constructed with a tank of water and a tank of molecular sieve X13 adsorption material connected through a vacuum valve. During the daytime, solar heat raised the temperature of the X13, liquid water ran out, and the X13 was dried. The vacuum valve was closed. In the evening, the X13 was cooled. The X13 stored heat and cold energy indefinitely. Later, when cooling or heating was needed, the vacuum valve was open, the X13 absorbed the vapor in the system, pressure dropped, surface of the water evaporated, vapor continued to absorb, carrying over 1,000 BTUs of energy per pound of vapor from the water to the X13. The water quickly froze and the X13 became hot. The ice then was used for cooling a house, and the X13 was available to heat a house. We had very good isotherms versus weight of water, as absorbed water, and pressure in the X13. Increasing the pressure or decreasing the temperature allowed more water to be stored in the X13. This is a criteria of gas, but not liquids. Water is a high density, low energy, ionized, gas-like fluid was exactly what trees needed. The graph shows isobars, showing one cycle of the solar-powered heat pump. Point A to point B shows 6 pounds of solar-driven water desorption. Point C to point D is 6 pounds of vapor moving over 6,000 BTUs of heat from the water to adsorbent, freezing 50 pounds of liquid water. Trees work this way. All of the proposed theories have a horrible mismatch of water pressure between the leaves and vapor in the atmosphere. The main reason there aren't solar-powered heat pumps on every house is our system was cycling too much dead weight. Commercial adsorbents hold up to about 25 pounds of water per 100 pounds of adsorbent. Roots can hold up to 400 pounds of water per 100 pounds of adsorbents. Roots are 16 times better than the adsorbent we use. They are very good isotherms plotted against pressure and magnitude of absorbed water and commercial adsorbents. There are no isotherm plots of water within tree roots. Here are some interesting theories that I've developed. First, I believe the above paragraphs are based on facts and physics. This paragraph is based on an interesting theory, but I have no data to back it up. I found it interesting that trees can contain so much water and still have great strength. As I pointed out above, adsorbed water is attached to the capillaries, which means the hydrogen atoms. The adsorbed layer of water does not have hydrogen atoms to hold molecules apart. Liquid water is very hard to compress, but vapor can easily be compressed. Adsorbed water is a low energy, high density gas-like fluid. Since adsorbed water has over 1,000 times less energy than vapor, maybe it can be compressed easily and weigh much more than 1 gram per cubic centimeter. The volume of water in trees may be much less than the weight indicates. This paragraph is also based on an interesting theory with no data to back it up. I once had a row of leaf lettuce growing next to the south-facing wall of our house. During December and January, the lettuce would be frozen early in the morning. By noon, the lettuce would be thawed in very good condition. This was strange, as when liquid water freezes, it expands and should destroy the leaf. My theory is that the lettuce only had adsorbed water, and maybe adsorbed water doesn't expand when it freezes. As I pointed out above, the capillaries are only 1 molecule in diameter. There is no liquid water in the plant. But if the capillaries are many molecules in diameter, there will be liquid water in the middle of the capillaries. Plants with large capillaries would be destroyed by freezing, but plants with very small capillaries might survive. This paragraph is also based on an interesting theory with no data to back it up. Most trees are dormant during the winter. That is, there are no leaves to perform transpiration or photosynthesis. However, in the spring, there's a sudden burst of leaf buds and blossoms. The absorption dispersion theory does not depend on leaves. It is always active, and as noted above, trees can absorb and hold more water as the temperature cools. The trees, therefore, have all winter to absorb and store energy, and since they are cold, they can store more energy than in the summer. As the summer progresses, magnitude of water stored in trees diminishes because the trees warm and growth slows. This slide of the rows shows absorption and cohesion. In this case, the cohesion is larger than absorption. The cohesion pulls the water into droplets, but there is adhesion because the droplets are not falling off, so it's attached to the rows. The capillary equation was developed by observation as the force was not known. Dispersion of gas-like water solves the force problem in the capillary equation. If the capillary diameter is 1 molecule, water will rise very high against gravity by dispersion. Gases always rise to fill the container, and gas-like water disperses up the glass. There is no need to push or pull the water. If the capillary diameter is several molecules in diameter, there will be additional molecules that are liquid, and the water will not rise so high as the molecules are pulled by gravity. The rise above the edge of the drinking glass of water is only about a millimeter because the active adsorbed molecules must drag many millions of liquid water molecules up the side of the glass and against gravity. This follows the capillary equation where the rise of water in the capillary is inversely in proportion to the diameter of the capillary. Note that the water rises highest in the smallest tube. The figure refers to contact angle and surface tension. These are both results and not forces. The absorbed water is dispersing up the tubes, dragging liquid water, causing the angles. There is no surface tension. The surface controlled by the glass tubes, molecular cohesion, gravity, and the dragging. I am surprised how often very smart professionals mistake a result for a force. I hope you have found this presentation interesting and that you carry these ideas forward. Presently, all biology and botany textbooks teach transpiration and lifting of liquid water in plants, which is proved wrong by basic physics. I am Charles Redmond. I hope you have found this presentation interesting, and I hope you carry these ideas forward.